Welcome back. Today, we are unpacking a truly revolutionary paper by Kyle MacLean-Smith titled Non-Infinite Quantum State Machines. We're going to explore a unique structural fix for one of the biggest, most persistent headaches in modern physics, the infinity problem in quantum mechanics. We're going to dive right into the geometry of all this and see how it completely changes the fundamental code of our systems. Let's get right into it. Okay, let's dive into this. Now, standard quantum electrodynamics, or QED, is incredibly precise, right? But at its core, it absolutely relies on mathematical magic tricks to fix equations that just naturally blow up into infinity. Basically, to get usable numbers, physicists have to subtract infinite quantities from other infinite quantities. Richard Feynman, who literally helped build this theory, absolutely hated this workaround. He famously called it hocus pocus and a dippy process. Well, the paper we're looking at today argues that we don't actually need these magic tricks at all, provided we just fix the underlying geometry. Here's a quick roadmap for this explainer. We'll start with the quantum infinity problem, move into the cycloidal bridge, look at sealing the torus hole, discuss how Achilles rides the tortoise, and finish up with the new rules of proof. I promise we're going to break this complex math down into really clear, manageable steps. All right, part one, the quantum infinity problem. So in standard quantum mechanics, our core mathematical villain is the zero-dimensional point. In QED, elementary particles are modeled as these pure 0D targets. Now the math works out beautifully from a distance, but as the interaction distance, which we represent with the variable r, approaches zero, the equations try to calculate self-energy by basically dividing by zero. And as we all know, dividing by zero breaks the system. It forces the theory to produce these crazy mathematical infinities, creating endless loops of unhalted drift. And that is exactly what requires that hocus-pocus renormalization we were just talking about. So look at the contrast here. Instead of the traditional model where zero-dimensional points force an infinite division by zero and unhalted drift, the author proposes replacing that entire concept with a continuous cycloidal logarithmic bridge. It's brilliant because instead of snapping to zero and breaking the math, the geometry just scales continuously. It entirely avoids those singular boundaries and ensures wave trajectories naturally converge on Fermat's path of least time. The result? Zero infinities generated, which means absolutely no renormalization is required. Which leads us to part two, the cycloidal bridge. And this brilliantly illustrates what that bridge actually looks like. In classical physics, the cycloid has two really fascinating properties. First, it's the brachistochrone. That means a curved path, rather than a straight line, is actually the fastest way through complex media without generating all that high latency and friction. Second, it's the tautochrone. This means if you drop an object anywhere along this curve, its time to convergence is identical. It is totally invariant of its starting point. In this framework, photons naturally follow this curve because it represents pure geometric efficiency. The straight line is simply the geometric limit of the cycloid as its radius approaches infinity. So photons are out there executing pure geometry, not some unhalted floating point drift. Mathematically, this happens in three clear steps. Step 1 introduces an invariant decay parameter, d, which is identically equal to the half-angle tangent tan theta over 2. Step 2 is where the magic happens. As our interaction distance r approaches zero, instead of hitting a brick wall and dividing by zero, the half-angle parameter smoothly and continuously scales. It just flattens right into a straight line at its limit. And step 3, the wave packet converges exactly onto Fermat's path of least time. Finite metrics are preserved from start to finish, the math stays perfectly intact, and we get no infinities. Moving right along to section 3, sealing the torus hole. Now, here's where the paper takes an amazing leap from theoretical physics straight into computing and system design. Think about modern computer architectures for a second. Traditional silicon allows continuous floating point drift, meaning code can easily get stuck in infinite execution loops. So the multi-million-dollar question becomes, using this cycloidal geometry, how do we physically and mathematically stop infinite drift? How do we force a deterministic halt so data doesn't just process endlessly into the void? The author solves this puzzle by defining a physical cap on the system, where capital D equals lowercase d to the power of n. In this specific manifold, there's an area duality between the total macro column and the capping block. D represents the quantized remaining area required to seal what the author calls the central torus hole. You can think of it like a literal physical plug for a leak in your system. As the step index n increments, the remaining area scales down deterministically until it reaches a bit-perfect cutoff. This forces the execution to stop exactly when it needs to. Boom, problem solved. This brings us to section 4, Achilles rides the tortoise.
Now, what's really interesting about this is how it flips an ancient philosophical concept totally on its head. You probably remember Zeno's paradox, right? Achilles endlessly chases a tortoise, having the distance over and over, essentially trapped in a decaying fraction of space forever. The paper argues that this represents unquantized infinite drift, basically a system that just accelerates forever without a boundary. But if we define our system with our equation capping the remaining area, we plug that torus hole. The area becomes deterministic. Because the system calculates a bit-perfect cutoff, Achilles is no longer endlessly chasing a decaying fraction of space. Instead, Achilles actually gets to ride the tortoise. The Zeno drift is completely halted, locking down a sovereign state.
And let me tell you, this matters way beyond the bounds of theoretical philosophy because this non-infinite state machine can be built into actual hardware, and even wetware. By sealing the torus hole and stopping that Zeno drift, this geometry literally halts infinite execution loops in our silicon architectures. It governs digital packet routing with absolute total precision. The paper even applies this to human attention, making the case that sealing unquantized execution spaces prevents cognitive fatigue and invasive data tracking. And on a purely thermodynamic level, a bit-perfect halt stops computer chips from over-accelerating and generating literal physical heat. It's a defensive architecture that reflects noise without burning out the substrate. It is a massive game changer. Which brings us to our final section, new rules of proof. So if you completely eliminate infinities without using those old subtraction tricks, you ultimately change how math itself is verified on paper. The author outlines some exact authoritative proof-closing conventions to replace the old QID tricks. First up, we keep the classic Halmos tombstone, the solid black square, but it's now strictly used to close exact algebraic and trigonometric identities. Next is QEF, which confirms practical hardware and state machine constructions. No more abstract thought experiments here. Did the circuit build or not? Then the phrase, the curve closes, signals that the wave has officially reached its cycloidal destination. And finally, the absolute mic drop for any academic debate. Math is math. It strips away all the rhetorical fluff, leaving only unyielding, working code. It's an incredibly bold framework that really forces us to rethink everything from fundamental particle physics to how our everyday processors handle basic loops. So I'll leave you with this. If we can mathematically seal the torus hole and guarantee a deterministic halt by passing that infinite drift that plagues standard equations, how will this curve-closing geometry redefine the absolute limits of our future cognitive and digital systems? It's a massive, fascinating question to ponder. Thank you so much for joining me on this explainer. Keep questioning the math, keep looking closely at the structures around you, and I will catch you in the next one.